In this outcome, we build the atom up from its subatomic particles, then see how the way electrons are arranged decides where each element sits in the periodic table. It's the foundation that everything else in chemistry rests on. Here's the ground we'll cover. We start inside the atom with the particles that make it up, their masses and charges, then move on to atomic number, mass number, isotopes, and relative atomic mass. From there, we work out electronic structure for elements up to element 36, link that arrangement to an element's place in the periodic table, and finish with the trends in ionization energy and reactivity. Let's begin right at the center. Every atom has a tiny, dense nucleus made of protons and neutrons, and around it electrons occupy shells, or energy levels. Almost all the mass is packed into that nucleus, while the atom as a whole is mostly empty space. And because the number of protons equals the number of electrons, the atom overall is electrically neutral. Now compare the three particles. A proton sits in the nucleus with a relative mass of 1 and a charge of +1. A neutron sits alongside it, also mass 1, but with no charge at all. The electron, out in the shells, carries a charge of -1 and a mass of only about 1/1836, so tiny we usually treat it as nothing. That's why the nucleus holds virtually all the mass. A few definitions worth fixing in your mind. The atomic number, Z, is the number of protons in the nucleus, and it's what defines the element. The mass number, A, is the total of protons and neutrons together. We call any proton or neutron a nucleon, and a neutral atom is simply one where the protons and electrons are equal in number. Let's put those two numbers to work. The atomic number, Z, counts the protons and tells you which element you've got. The mass number, A, is protons plus neutrons, so the number of neutrons is just A minus Z. We write it with the mass number on top and the atomic number below the symbol, so iron appears as 56 on top, 26 below. And in a neutral atom, the number of electrons matches Z. Let's count the particles in an iron atom, with atomic number 26 and mass number 56. The protons come straight from the atomic number, so that's 26. Since the atom is neutral, the electrons match, another 26. And the neutrons are the mass number minus the atomic number. 56 take away 26, which is 30. So iron has 26 protons, 26 electrons, and 30 neutrons. Here's a subtlety. Isotopes are atoms of the same element that have different masses. They carry the same number of protons, so the same atomic number, but different numbers of neutrons. Because their electron arrangement is identical, they react in exactly the same way chemically, though physical properties like density differ slightly. Take the two isotopes of chlorine, chlorine 35 and chlorine 37, both with atomic number 17. Each has 17 protons and 17 electrons, since they're the same element. For chlorine 35, the neutrons are 35 minus 17, so 18. For chlorine 37, it's 37 minus 17, so 20. The only difference between them is those two extra neutrons. Time for a few more terms. An isotope, as we've seen, is an atom with the same protons but a different number of neutrons. Relative atomic mass, written AR, is the mean mass of an atom compared with 1/12, the mass of a carbon-12 atom. The isotopic mass is the mass of one particular isotope on that same scale, and abundance is the percentage of each isotope you find in a natural sample. So, relative atomic mass is really a weighted average. It takes every isotope of an element and accounts for how common each one is, its abundance. The scale is set so that carbon-12 is exactly 12, and because it's a ratio, AR has no units. That weighting is exactly why so many relative atomic masses come out as awkward, non-whole numbers. Let's calculate the relative atomic mass of chlorine, which is 75% chlorine 35 and 25% chlorine 37. You multiply each mass by its abundance, add those together, then divide by 100. So that's 35 times 75 plus 37 times 25, which gives 2,625 plus 925, so 3,550. Divide by 100 and the relative atomic mass comes out at 35.5. Let's pause and test yourself. First, how many neutrons are in an atom of potassium-39, which has atomic number 19? Second, why do two isotopes of an element react in exactly the same way? Third, boron is 19.9% boron-10 and 80.1% boron-11, so what's its relative atomic mass to one decimal place? And finally, why are relative atomic masses so rarely whole numbers? Have a think before moving on. Now, let's look more closely at where the electrons live. They occupy shells, also called energy levels, and the further a shell is from the nucleus, the higher its energy. Each shell is divided into subshells, which are themselves made up of orbitals, and every orbital can hold up to 2 electrons. The subshell types we'll meet here are the S, P, and D types. Let's see how much each subshell can hold. The S subshell has just 1 orbital, so it holds 2 electrons. The P subshell has 3 orbitals, holding 6 electrons in total, and the D subshell has 5 orbitals, so it takes up to 10. Remember, it's 2 electrons per orbital every time. That's the pattern underneath all of it. Electrons always fill the lowest energy subshell available first. The order runs 1s, 2s, 2p, 3s, 3p, then 4s, then 3d, then 4p. Notice that 4s slips in below 3d. It's actually lower in energy, so 4s fills before 3d for the elements after argon. That little bit of overlap is what gives the periodic table its shape. Let's write the full electronic structure of calcium, which has 20 electrons. We fill in energy order 1s, 2s, 2p, 3s, 3p, then 4s. So 1s2, 2s2, 2p6 gives us 10 electrons, 3s2, 3p6 adds another 8, bringing us to 18. And the final 4s2 adds the last 2. So calcium is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Bromine, with 35 electrons, is a good test of that 4s before 3d rule. Start by filling up to argon. 1s2, 2s2, 2p6, 3s2, 3pa6, that's 18 electrons. Next comes 4s2, taking us to 20. Then the 3d fills with 10 electrons, giving 30. The remaining 5 electrons go into 4p, so 4p5. Written out, bromine is 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s2, 4p5. There are 2 famous exceptions worth knowing. A half-full or a completely full D subshell turns out to be especially stable, and 2 elements take advantage of this. Chromium ends up as 3d5, 4s1, rather than the 3d4, 4s2 you'd expect, and copper becomes 3d10, 4s1, instead of 3d9, 4s2. In each case, one 4s electron shifts into the 3d for extra stability, and these are the only 2 exceptions up to element 36. Let's write those 2 out in full. For chromium, atomic number 24, you'd expect it to end 3d4, 4s2, but one 4s electron moves across, giving chromium as 1s2, 2s2, 2p6, 3s2, 3p6, 3d5, 4s1 with a stable half-full D. Copper, atomic number 29, would be expected to end 3d9, 4s2, but again an electron shifts, so copper is 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s1 with a full D subshell. Each gains its stability from that half-full or full 3d. Here's the neat link between electron arrangement and the periodic table. The period number tells you the highest occupied shell, while the group number is tied to the number of outer shell electrons. Elements filling s orbitals make up the s block, which is groups 1 and 2. Those filling p orbitals form the p block, groups 3 across to 0. And the elements filling the 3d subshell are the d block, the transition metals. Let's ground that with examples. In the s block, the outer electrons sit in an s orbital, like sodium, 1s2, 2s2, 2p6, 3s1, sitting in group 1. In the p block, the outer electrons are in a p orbital, like chlorine, ending 3s2, 3p5 in group 7. And in the d block, the 3d subshell is filling, like iron, which ends 3d6, 4s2. The outer electron arrangement places each element exactly where it belongs. Ionization energy is a measure of how tightly an atom holds its outer electron. Specifically, the first ionization energy is the energy needed to remove 1 mole of electrons from 1 mole of gaseous atoms. Written m gas goes to m plus gas plus an electron. It's measured in kilojoules per mole, and a higher value means the outer electron is held more tightly. It depends on the nuclear charge, the distance out to the electron, and the shielding from inner shells. 2 trends are worth knowing. Going down group 1, the first ionization energy falls because the outer electron is further out and better shielded by inner shells, so it's easier to remove. Going across period 3, from sodium to argon, it generally rises because more protons pull the outer electrons, which are in the same shell, in more tightly. There are small dips, though, at aluminium, where a 3p electron starts, and at sulfur, because of repulsion between paired 3p electrons. Let's reason through one of those dips. Why is aluminium's first ionization energy lower than magnesium's, even though aluminium has more protons? Magnesium's outer electron comes out of a 3s orbital, whereas aluminium's comes from a higher energy 3p orbital. That 3p electron is slightly further out and is shielded by the 3s electrons, so despite the extra proton, it's held less tightly and needs less energy to remove. That's the reason for the dip. Now let's connect this to reactivity. Group 1 metals react by losing their single outer electron. As you go down the group, that outer electron sits further from the nucleus, and with more inner shells, the shielding increases, weakening the attraction. So the first ionization energy falls, the electron is lost more easily, and the metals get more reactive. Sodium with water, for instance, gives 2 sodium, plus 2 water goes to 2 sodium hydroxide, plus hydrogen gas. Group 7 works the other way. These non-metals react by gaining an electron, forming 1- ions like chloride and bromide. As you go down the group, the atom gets larger and there's more shielding, so the nucleus attracts an incoming electron less strongly. That makes gaining an electron harder, and so reactivity falls as you descend the group, the opposite trend to the metals. Time to check your understanding again. First, write out the full electronic configuration of iron atomic number 26. Second, why does chromium adopt 3d5, 4s1 rather than 3d4, 4s2? Third, explain why the first ionization energy decreases down group 1. And fourth, why does the reactivity of group 7 elements decrease down the group? Take a moment with each.